healthcare. What does it require? Do you think like it won't require mathematics? Typical thought process when we are kids or any of you are kids. Because I want to do medicine, I don't need to study mathematics. But that's also not the case. So, whenever you are trying to address bigger challenges of the society, it requires knowledge of multiple disciplines, and when you are addressing it, you need to apply it effectively in such a manner that your solution become robust enough. So, we'll talk about three solutions, three of my projects that we have been working currently, and we will see like how AI can play a role in addressing such bigger challenges of the society. How those can be disruptive in a way which will transform the whole field and whole area as well. Let's have a look. Right. So, why do we need AI first of all? Let's say we have a cockroach at home and we want to get rid of it. What do we do? Do we take a hammer and run behind it? Do we use a cannon and go behind it? Do we use something bigger? We don't, right? We'll use some tiny tool, which is even a slipper or that much tiny. So, can we use AI for each and every problem? And is it wise to use AI for each and every problem? Then one use case which is obvious is go for something which is not doable by our normal capacity or by our normal intelligence. Of course, you can do the things to speed up your task, but if you use it for such things which are otherwise not possible, then it will add a lot more when you do it. So if we look into MRI and histopathology, where the tissue specimens are observed or organs imaging has been performed, afterwards if you need to analyze them, for that if you utilize AI or design new AI tools, that's a wiser use. Otherwise it will be running behind a cockroach with a hammer. It will not make everyone happy at home, or the other people or the neighbors not happy at home. Right, so how can we use AI and computer vision? So computer vision again is a very parallel branch which helps AI to become more and more better. So it basically deals with images, videos and all those aspects. And it helps in addressing the bigger challenges of the society. So now let's have a look at one of the challenges.
Imagine a world where medical diagnoses are faster, cheaper, and more accessible. Welcome to the future of pathology, where artificial intelligence is revolutionizing how we view and study tissue samples. In traditional pathology, tissue samples are stained with chemicals to highlight cells under a microscope. But this process is time-consuming, expensive, and requires specialized labs. What if we could virtually stain these tissues, without chemicals, and without harming the samples? Thanks to advances in deep learning, this is now possible. Our project uses AI to create these stains digitally, completely skipping the chemical process. Why does this matter? Physical staining limits access in remote or low-resource areas. It also slows down urgent diagnoses, like cancer detection. Our AI-driven virtual staining can make pathology faster, more affordable, and available anywhere, helping doctors save lives. How do we do it? We use a deep learning model called CycleGAN. Unlike many models that need exact, before and after pairs to learn, CycleGAN can teach itself how to translate between two types of images, unstained and stained, even if they aren't perfectly matched. It learns by making sure that if you go from one domain to the other and back again, you end up where you started, preserving key information in the process. We began by preparing a dataset of tissue images, carefully dividing them into small patches for training. The images were aligned to ensure important structures matched accurately. Then, the CycleGAN model was trained to generate virtually stained images by balancing two forces. One part tried to fool the AI into believing the generated images were real, while the other ensured that important tissue details were preserved. The results? They are impressive. Our CycleGAN model produces virtual stains that closely match real H and E stained images, making them reliable for pathologists. It's faster, safer, and opens new possibilities for diagnostics and research, all while reducing costs and chemical usage. With AI-powered virtual staining, we're making pathology more efficient and accessible, saving valuable samples, reducing chemical waste, and speeding up diagnosis. As As the technology advances, it holds the potential to become a trusted part of real-world healthcare.
Right, now let's look deeper into the actual problem statement. So what this model or what has been described here is trying to color the images. Basically, when you go to a laboratory, you will get your tissues examined under a microscope, and an image of those tissues will be taken by them and they will process it in the computer. Not all the pathologists or not all the laboratories will do that. Some advanced laboratories do that. Most of the routine ones, they don't do. But those who do, they additionally need more. They need to observe the details under the microscope in such a manner that the results will be accurate or the assessment will be accurate. How they can do that? For that, they need good contrast within those tissues or within those features. Now, if you want good contrast out of it, you can do it two ways. Either add something which will highlight both of the features or all the features in such a manner that you will easily be able to see them. Or, second approach, digitally add the contrast. Now, how you can do the digital? So that's how the AI will be taking it. First, let's explore what are the limitations of manually dyeing it. So basically, in current practice, they put some dye, they procure that dye and they put it into it so that the tissues will get highlighted, and afterwards they will be able to do the analysis based on that. But in this process, they need to first procure the dye from somewhere. So if you consider a typical city, there will be hundreds of laboratories, and if you combine procurement of the dye, that will go quite a lot. And again, to recycle or to discard or to get rid of the dye from the planet, it's a bigger cost. So it's again a environmental burden or a burden on the planet from the environment side as well. Now the researchers have come up with a new technique which is called generative adversarial network based virtual staining. So it's called virtual staining itself, where you don't need the dye at all. You can simply have an AI based model. So here the AI is generative adversarial network. This typical model was cycle chain, but there are other models as well which can help you design your problem solution in such a manner. So what it does is, or what it has is, two AI models. So far, think of you have ChatGPT and you have Gemini. Both are fighting with each other, and you are trying to achieve your objective out of it. So some people do that, like generate prompts using ChatGPT, give those prompts to the Gemini, and then they try to refine their output. So similarly, here we have two models. One is generator, another is discriminator. So generator tries to mimic how the colored image look like or how the contrasted image look like, and discriminator will already have such database which will try to differentiate whether it is real or not. And accordingly, with this game, over the time the model will get trained with hundreds of samples or thousands of samples, and it will try to achieve accuracy in a much more better and much more rigorous manner, and it will ultimately give you the outcome which is much more similar to what the stained sample look like. So that's one of the use case that we can think of. But imagine the impact. So if you don't need to procure that much of dye, that means you will reduce the procurement cost. You will also reduce the environmental impact. You will also need not to have advanced machinery to process those samples, and you will directly be able to get the outcome through what you have done digitally. So that's where it makes a bigger difference, and that's how it disrupts the routine process or routine pipeline of work. Now let's have a look at the another one. Right. Tumor. Again, bigger challenge in the society, much larger. So cardiovascular disease are the biggest killer in the world. Second biggest, cancers, whether it is brain or liver or any other organ. And nowadays also eye cancers are also rising. So that is also another area. But thing is, how do you assess it or how do you diagnose it effectively? So in also people don't directly just come up with cancer, right? First they will have some symptoms, let's say headache or some other, and they will go to the neurologist, and neurologist will refer that go get an MRI done, and after that we'll visualize it and we'll figure it out like what it is and how severe it is. So during that assessment, they need to find out how big is the tumor. So to be able to understand the severity of the tumor, size is one of the parameter or one of the criteria or biomarker. Then how aggressively is it growing, then how big is the periphery and the other components. So all of these are different components for the same patient, for the same image. So in this type of MRI, flare MRI, it shows something else, T1 weighted MRI, something else, gadolinium enhanced T1 weighted MRI, it shows different feature, and T2 weighted MRI, it again shows different feature. But all four of them combinedly adds to the diagnosis, and it will help you determine how severe is the tumor. Now, such applications empower neurologists or the radiologists to make an informed decision out of it. But will they be able to do it in a timely manner? That's again a question. Because here, each of them is not just one 2D image, each of them are 3D volumes. So 3D volume means 100 by 50 by 100 by 50 by 100 by 50. And manually identifying how big is the tumor in each and every image will take days. And hospital will not have just one patient, right? They will have plenty of patients, and they need to solve all of them and also need to solve them effectively. It can't be a big decision. So how technology can help in such cases? How technology can help do it in a much more efficient and much more rigorous manner and more in a more less time consuming manner. So for that again, AI can help. Why? Because segmentation is a very classical problem in computer vision since many years. And after the AI models evolution and after the AI models came into picture, the segmentation architectures have also improvised quite a lot. So one such architecture or one such design I can show here. So this is also from one of our previous work. So here all four types of MRI, you can give it to the AI model. It will extract all the features, learn different parameters out of it, and ultimately will give you the segmented results out of it. So the AI model will segment it with quite a good accuracy to a level which will be useful for radiologists to further refine it. So that will make the task much faster and much more efficient. Otherwise, if they will do it manually, it's almost not feasible or not possible to complete it in time. But that's not the end, that's just the step one. Because how severe is the tumor? That depends on many other things as well. So for example, here we have additionally extracted features out of it. So features are radiomics features which we can't directly see otherwise. But images will have the features or the patterns inside it. So to be able to understand that, there are set of features called radiomics features, and they can be extracted using image processing algorithms and other techniques to understand what are the values around it. And then they can be further fed to classification and typical regression or any other machine learning models, random forest or any other, to understand how the ultimately tumor is being considered as severe. And also, if the tumor has been treated and the patient has come for a follow-up, it can help in predicting survival days. So how much time or how based on the previous treatment, how much the time the patient has for the next treatment or for the next chances of getting the tumor. So that also helps in assessing the treatment response, which is also quite an important factor for a patient perspective, because the patient also needs to know whether the tumor will happen again or not, what are the chances or not. So that's where the AI can also come into picture. But again, another common thing, the AI is a black box. So people don't trust it, or we don't really directly trust it, because it's a completely different one, how the decision has been made. So for that there are additional XAI model, so explainable AI, which will take through the whole procedure in a manner and show the features like why that type of decision is being given by this particular AI model. What is the underlying biological phenomena which has been considered to give reason for this particular decision. So that's also another AI component that typically comes in a design solution for the tumor diagnosis, or in general for the diagnosis. Right. So here, so this is just one case study out of our database that we have earlier. So here, you will be able to see three tumor components. The outer side is bigger, which is called peritumoral edema. Inner one, tumor core, and within that, the enhanced tumor core with the highlighted boundary. And these all are different types of MRI, because this information will be quite essential for the person or for the neurologist to make a decision whether the person needs to be treated with this much of chemotherapy or that much of chemotherapy. If they will over-treat it, it's an issue. If they under-treat it, still it's an issue. So they have to be very precise how much dose they are giving and how they are treating overall. Right. Another thing, how AI can help us access the details which otherwise is not possible or otherwise we can't. So we have tissue. Within the tissue, there are cells. Within the cells, there are genes. So in each cell, typically, let's say there are 20,000 genes by normal, and there are additionally 20 more thousand genes are also there. Now, if we want to understand how the distribution is of the gene, then will it help us, or how we can do that? Because whenever someone has cancer or some other abnormality, there will be particular genes which are showing those characteristics or which are responsible to show that this cell is affected, or here is the gene which is of trouble. So how to find them or how to reach to that level of detail? So again, there are this one is also AI based model that we developed. So here this is HNE stain microscopy image, and that one is a special transcriptomics data. So to acquire that type of image from the instrument itself is a bigger challenge and bigger task, and then map it in a manner that will give you distribution of each gene per cell. So it will clearly differentiate like different genes with different colors, and ultimately it can help understand like whether there is a troublesome gene in this cell or not, and how you can do the underlying biological process based on that, and accordingly simulate whatever the ultimate outcome you want to achieve. So these are three of the use cases that are quite like in a recent time quite cutting edge, where AI